Let's now look at this idea of quadratic denominators. Because we saw with the partial fractions we can break everything down to be linear factors or quadratic factors. Linear, nice and easy, they're always log. But quadratics, those quadratics that can't be factorized, what happens to them? Well, we've got a couple of possibilities. Maybe they could be factorized and we end up with a difference of two squares situation. So in that case you could use partial fractions and you would end up with this. Now my suggestion to you is don't do it by partial fractions every time, just remember this, because that's going to save you a lot of time. You don't have to worry about partial fractions, go straight into the standard integral. Okay? When we do an example later, I'll show you how you remember the difference between the two. Okay, what else could it be? Well, it might end up being the sum of two squares, which of course can't be factorized. That's the inverse tan, of course. So we can handle that one. Well, what about if it's the square root of a quadratic? Well, inverse sine or negative inverse cos, we know that one, if it's the square root of a squared minus x squared. But then we have the missing integrals that I was telling you about, but remembering them, the structure is essentially the same, it's just that the square root matches the square root. Okay, so we get something like this, 5 over x squared plus 4x plus 9. So we want to turn the denominator into either the sum of two squares or the difference of two squares. We do that by completing the square. Complete the square, we get x plus 2 squared plus 5. So it's the sum of two squares, which we know is inverse tan. So I have inverse tan. Okay, it's x plus 2 instead of x, but that's fine. So it becomes 5 times 1 on root 5 inverse tan, x plus 2 over root 5. 3x plus 2 on the square root of x squared minus 4x plus 1. This is how we do it. I break it up into two integrals. The first integral has the derivative on the top. So the derivative of x squared minus 4x plus 1 is 2x minus 4. So I create the derivative on top because I'm basically forcing it to be du on root u, which I know is 2 root u. Forcing it. Now obviously I can't change the number. It's 3x, not 2x. So I've got to multiply that by 3 on 2. But my number now is not 2. It's 3 on 2 times negative 4, which is negative 6. So to get it back to the 2 that I want, the second integral just has the constant 8 on top. So the very first fraction I can handle, that's du on root u. The second one is where I'm going to complete the square. If you don't see the du on root u, then alright, you do your substitution for the first one, but you end up with du on root u. The second one is what I'm interested in now. I'll complete the square on that, and I get x minus 2 squared minus 3. So it's in the form the square root of x squared minus a squared. So it's in the form log of x, in this case x minus 2, plus the square root, the same square root that was in the integral. So the square root of x squared minus 4x plus 1. Out the front here, remember that's 2 root u, but times it by the 3 on 2, we get 3 root u. There's our final answer. Hang on, I thought you said this was quadratic denominators. I can turn it into a quadratic denominator question by multiplying by not the square root of the denominator, but the square root of the numerator. By doing that, I've turned it into a question I can handle. Split it into two. The first one, create the derivative. The derivative would be minus 2x minus 1. But it was x, not minus 2x, so I've got to multiply by minus a half. My constant is now positive a half. I want it to be 3. So I've got to add 5 on 2. It's the denominator that I'm interested in. The first one I've created, du on root u. Again, if you don't see it, you do your substitution. But it is completing the square. You've got to be real careful with this one. When we complete the square, we know we're going to get x and then half the coefficient of x all squared. In this case, the coefficient of x is negative 1. But you'll notice I put positive a half. Why? Because when I expand out, I get negative x squared. Therefore, there must have been a negative out the front of this perfect square. Which means when I expand this out, I don't want a negative twice the product. I want a positive twice the product. Be really, really careful with your signs there. Maybe even do that mental check to make sure. Hang on. Oh, good. It is negative. But now I've got it in the form I want. because it is in the square root of a squared minus x squared, which was, that's inverse sine, isn't it? So we have inverse sine. So the first one goes to 2 root u, the second one goes to inverse sine. We can make that look better. 2x plus 1 on 5. So those missing standard integrals. But the difference of two squares. I said a squared minus x squared ends up being that. How do I know it's that one? Well, have a look. It finished with x, or more to the point, it finished with negative x. Therefore, when I write this log down, I finish with negative x. So I know because I'm finishing with negative x, the top must have gone a plus x, the bottom goes a minus x. The other one is x squared minus a squared. Look at that. It begins with x. So because I begin with x, I start with x and go x minus a. The other one must be x plus a. So it begins with the x minus a. That's how I remember which way around it goes. Because other than that, they're both 1 on 2a, the log of that particular expression. Exercise 4e we'll add to our list there.